Okay, good morning. Okay, so let's start the class. So today we will continue our discussion on the generating function. So our target is to show you in some way that we can use generating function to solve counting problems. But before that, because we are going to use binomial theorem quite often, so I will review the generalized binomial theorem to you first. But before that, you may know this or you may not know this before, never mind. But first of all, let me review the Maclurin series of a function. So let me have a double check. If you still recall what is meant by Maclurin series, could you please raise your hand? Hey, good. Nobody. That's good. On the other hand, okay, when I tell you, you must be able to. How about Taylor's expansion? Taylor series? Okay. Maclurin series is the special case of a Taylor's expansion. That's no problem. So here, suppose that we have a function x. Perhaps it is a sine x or cosine x or maybe log x or whatever. So we have a certain function. This function may not be a polynomial, but we want to estimate it by a polynomial. So this is quite often used. So for instance, we may approximate a log of x, something like 1 plus x plus 1 over 2 factorial times x squared plus 1 over 3 factorial times x cubed, and so on and so forth. Okay? So how do we get this? So the idea is like this. So we assume that this fx can really be represented by a certain polynomial in x, like some constant c0 plus c1 times x plus c2 times x squared plus c3 times x cubed, and so on and so forth. Okay? And now, how do we know what is this value of c0? So how do we get c0? If I am assuming that fx looks like this, so how do we get c0? So you want to make sure that these terms go away, right? So you put x to be 0. Am I correct? Good. Excellent. So this term is what? Is f of 0. Is that okay? Okay. And then how do we get c1? So to get c1, how do we get c1? Okay. So we differentiate the thing once. Okay. So we differentiate it once. What do we get? We get c1 plus 2 times c2x plus 3 times c3x squared plus 4 times c4x x cubed, and so on and so forth. Am I correct? Okay. And then we want to get the constant term of the differentiation of fx. So how do we get? So this is going to be, you differentiate it once and you substitute x to be 0 inside. Is that okay? Okay, good. So this is going to be f prime 0. Is that okay? You differentiate it once and then you substitute x to be 0 there. Is that okay? Now how about this? So continuing with our idea, so to get c2, we differentiate the whole thing twice and put x to be 0, right? So we hope to get this to be f, you differentiate twice, and then you get x to be 0. But there is a problem. There is a problem because when you differentiate it twice, you are differentiate the first time, it is not c2 times x anymore, it is 2 times c2x, right? So you need to divide it by 2 in order to make it correct. Is that okay? And how about this one? This one is similar. You differentiate it 3 times, but by differentiating 3 times, in doing so, you get a 3 and then you get a 2. So you should divide it by 3 times 2. Is that okay? So in general, if you differentiate it k times, you need to divide it by k factorial. Is that okay? So and then this is the Maclurin series. Okay. So the Maclurin series will be equal to, so this is going to be f0 plus f prime 0 x. So what is the coefficient of x? F prime 0 plus f double prime 0 divided by 2 factorial x squared plus dot dot dot. And in general, if you want to look at the coefficient of x to the power k, then that's easy. You differentiate the function k times, find out what is the value when x is 0, and then multiply by x to the power k. That's it. Is that okay? Okay. So this is a special case of the Taylor's expansion. So this is the Taylor's expansion at the point x is equal to 0. So you can do something fancy. So you can think of this as a function not in terms of x, but in terms of something like so. So when we talk about Taylor's expansion, we think of this function as something a different way. So if you look at Taylor's expansion, so we hope to think of this as a function of some other constant, let's say d0 plus d1, but I don't like x. I like x minus c plus d2 x minus c squared plus d3 x minus c cube, and so on and so forth. We think of this as something like this. And then, how do we get d0? How do we get d0? What is d0? How do I get d0? So what should I do? fc, right? So this is going to be f of c. Is that okay? How do I get d1? You differentiate it once and put c inside. So this is going to be f prime c. Is that okay? How do I get d2? So I differentiate it twice and divide it by 2 factorial. Is that okay? So that's it. So in the end, then, if for general Taylor's expansion, then we get this is going to be f of c plus f prime c times x minus c plus dot dot dot, and in general it is f double prime, not double prime, f you differentiate it k times, you substitute x is equal to c there, divided by k factorial times x minus c to the power k dot dot dot. Is that okay? Okay. So the purpose of having this one is what? You can use the local property. You just focus on the function at the point x is equal to 0 here, or x is equal to c here, and get the estimation. Okay. If you have the first derivative, you get more accurate estimation, and so on and so forth. Okay. Now, why should I introduce this Maclurin series? Because it is helpful in getting the generalized binomial theorem. Okay. So here, this is 1 plus x to the power r, where r is a real number. And then I want to express this. So if r is a positive integer, then we know what? We know that this is going to be, so if r is a positive integer, then we know exactly what is 1 plus x to the power r. Is that okay? Because it is going to be 1 plus r choose 1 times x, plus r choose 2 times x squared, plus r choose 3 times x cubed, and so on and so forth. But consider an example. So today, let's say I'm going to look at 1 plus x to the power 0.1. Then what would it be? Or 1 plus x to the power minus 4. What would that be? Okay. So this is no longer a polynomial, but we want to estimate it using a polynomial. So we use the Maclurin series. And let's see. Okay. Let's use our brain. Okay. So in the Maclurin series, so I hope to get it into some term plus some other term times x plus some other term times x squared and so on. Is that okay? Okay. And now, how do we get the constant term? So to get the constant term, I just substitute x to be 0 here inside. Am I correct? And then I get it. So it is equal to 1. Is that okay? And then to get the coefficient of x, I differentiate it once. So I will get r times 1 plus x to the power r minus 1. So differentiate it once. So you differentiate once, you get something like 1 plus x to the power r minus 1. I have a r here. Is that okay? And then I substitute x is equal to 0. Put it there. So I will get r times x. Is that okay? And then how about this one? This one, I differentiate it twice. Okay, I differentiate it twice. And then substitute x is equal to 0 and divide it by 2 factorial. Okay, so we don't want to forget we should divide this by 2 factorial. So you differentiate it again. So you differentiate again. So you get r times r minus 1 times 1 plus x to the power r minus 2. Am I correct? You put x to be 0 there, so you get r times r minus 1. Okay? So you get r times r minus 1 divided by 2 factorial x squared. Is that okay? And in general, if it is the kth term, you get r minus 1 blah 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 divided by k factorial x to the power k. And then altogether, there are going to be k terms here. Is that okay? Is that okay? So that's it. So this is the so-called generalized binomial theorem. So whenever this is a real number, then we can do this. Is that okay? And then this one, let me define a shorthand notation for this. So this one is, you start with a term r, and then you have the next one r minus 1, and then you have the next term r minus 2, and so on and so forth. Each term, it is 1 less than the previous term. And let's say there are k terms there. I will call this r to the power k falling. So this is called the falling function, the k falling power of r. Okay, so it is like if every term is r, then it is r to the power k. But it is not. So the next term is 1 less than the previous term. And then the next term is 1 less than its previous term. So I call it r k, something like this. Is that okay? And then what do we know? And what do we know? If I have nk, this one, divided by k factorial, where n is an integer, then this is exactly equal to n choose k. Is that okay? Is that okay? So what is n choose k? What is n choose k? N choose k. So let me write on the board here. What is n choose k? So n choose k is equal to what? N factorial divided by k factorial n minus k factorial. Am I correct? Is that okay? So n factorial divided by n minus k factorial is, you start with n minus 1, and you cancel out the last n minus k terms. So what is left? What is left? There are only k terms left here. Is that okay? And then this one, this is equal to, by our notation, it is n to the power k falling divided by k factorial. Is that okay? Is that okay? Okay, so if it is like this, let us generalize this not only for n, but we can define a notation for any r, real number, and then we define something called r choose k to be equal to r to the power k falling divided by k factorial. Is that okay? Now, if we define something like this, then we have a very nice way of writing the generalized binomial theorem. It is just a very nice way to write this down. So let me remove it. So this will be equal to what? This will be equal to 1 plus r choose 1 x plus r choose 2 x squared plus dot dot dot. Is that okay? Okay, so that's all. That's all I want to introduce for the generalized binomial theorem. But in any case, if you don't like this, you can recall that this looks like this form. Okay? Okay, so next, let's start to use the generating function to solve counting problems. Okay, so we have this example. So suppose that what? Suppose there are P types of objects. Oh, let's say R types of objects. Okay. Suppose that there are R types of objects. Is it R? Let me see. Suppose that there are. Let me see what is the best notation for me. Suppose that there are. Okay, suppose that there are R types of objects. No. N. Sorry. Suppose that there are N types of objects. Okay. Sorry. Let me see. Let me see which one is the best to whatever. N types of objects. Each with unlimited supply. How many ways? How many ways to choose R objects? Okay, so let's say we have apples, oranges, bananas. Oh no, pears. Okay, apples, oranges, bananas. Pears. Sorry, 4 things. Apples, orange, bananas, and pears, okay? And then we want to get a total of 5 objects. So I may get 2 apples, 3 oranges. This is one method. I may get 1 apple, 1 orange, 1 banana, and 2 pears. This is another way, right? So we have studied this problem before, exactly, right? So we can use a balls and bars model to do the counting. But let's solve this problem again using the generating function, okay? So first of all, there are N types of objects, each with unlimited supply. So in our case, so we can look at object 1. What is the generating function of object 1? And then object 2, what is the generating function of object 2? And so on and so forth. And then for each selection that we are going to make, we are going to decide how do we select the first type of object, like let's say apples, and then how do we select the second type of objects, and so on and so forth. So we multiply these generating functions together, it will mean the generating function of how we can select. Okay? Okay, so let's see. Let's test our understanding. So let's focus on apples. Let's say apple is the first type of object. So we are going to find a generating function of selecting apple. So for apple, it has unlimited supply, right? How many ways, just for apples, how many ways in our selection that we can take, just look at apples, forget about oranges, bananas, everything else. How many ways that we can select 0 apples? How many ways are there? One way, right? There's just one way of selecting 0 apples. How many ways of selecting 1 apple? One way, right? Yeah, we select one. This is just one way. How many ways to select 2 apples? How many ways to select 2 apples? Yeah, one way. I select 2 apples. This is the only way. It's not like I have a red apple and then a green apple or 2 green apples. It's not like that. I have just one way. Okay, all apples are the same. So there's just one way of selecting 2 apples, and then one way to select 3 apples, and so on and so forth. Is that okay? So this is the generating function for apples. And then we should have a generating function for the second type of object, the orange, right? So for the orange, it is also the same, right? One way to select one orange, one way to select 0 orange, one way to select 1 orange, one way to select 2 oranges, and so on and so forth. Is that okay? And so on and so forth. And for this particular problem, the generating function of selecting object is equal to 1 plus x squared plus x cubed plus ... to the power n. Does that make sense? Does that make sense? Okay, good. And then what we are interested. So this is a generating function about selecting from n types of objects that has this requirement. And then we want to find out how many ways to choose R objects. So our focus is, so this one, the number of ways will be equal to the coefficient of x to the power r in this generating function. Is that okay? Okay. So we want to find out what is the coefficient of x to the power r here. So we want to find out what is it.